Welcome back to the AI Research Roundup. I'm Alex, and today we're diving into a paper published on May 7th, 2025, titled Registration of 3D Point Sets Using Exponential-based Similarity Matrix. So this research tackles a really common challenge in computer vision and robotics, which is point cloud registration. That's essentially the task of aligning different 3D scans of an object or environment, like data captured by LiDAR. The paper proposes a new method called Exponential Similarity Matrix Iterative Closest Point, or ESMICP, which is a modification of the well-known Iterative Closest Point algorithm. The core idea is to use a special similarity matrix, which is a way to measure how alike points are in different scans, built with an exponential weighting scheme to better handle tricky situations like large rotations between scans, or when the data has non-Gaussian noise, which is a type of unpredictable sensor error. And it's great to see they've also released the code for this exponential similarity matrix iterative closest point work on GitHub. So the repository primarily contains their C++ implementation of the algorithm. You'll find tools for aligning these 3D point clouds, a demo viewer, and even code for comparing its performance against other methods. Alright, and speaking of aligning those 3D point clouds, Figure 1 here gives us a great visual demonstration of the exponential similarity matrix iterative closest point method in action. So in the top row of the figure, we have these input pairs. You can see for different objects, like the Stanford bunny, a potted plant, and a dispenser-like shape, there are two sets of points, one shown in green and one in red, representing the initial misaligned 3D scans. Then, the bottom row shows the ESMICP output, and here those green and red point clouds are now really well overlaid, demonstrating a successful alignment of the objects. Alright, so building on that idea of successful alignment, we saw with different objects. Figure 2 here zooms in specifically on the Stanford bunny again, but what's new is that it shows us the alignment process unfolding over iterations, even with a significant initial misalignment. Panel A shows the initial red source and green target point clouds, quite far apart. The description notes, these have been downsampled using voxel grid filtering, which is a technique that simplifies the point cloud by dividing the 3D space into little cubes or voxels, and then representing the points within each cube by a single point. Then, panel B shows the alignment getting much better after 14 iterations, and by panel C, after just one more iteration, making it 15, they're very well aligned. Okay, so after seeing how exponential similarity matrix iterative closest point handles a single object like the bunny, Figure 4 now broadens the view by visually comparing its alignment results against other, what are called geometric-based approaches. These are traditional methods that rely on the shape and geometry of the point clouds to find the alignment. We've got three different objects here: an airplane in the top row, a person in the middle, and a desk-like shape at the bottom. For each object, the first column shows that initial severe misalignment. Then, the subsequent columns display results from various methods, and if you look at the far right column for each object, that's where exponential similarity matrix iterative closest point really shines, showing a much tighter and more accurate alignment compared to the others. Okay, so we've seen how exponential similarity matrix iterative closest point stacks up against traditional geometric methods. Now, Figure 5 shifts the focus to compare its performance against several deep learning approaches. So, these are methods that learn to align point clouds, often from large datasets, rather than relying purely on geometric calculations. Again, we see three different objects: a chair in the top row, a guitar in the middle, and what looks like another type of chair or stool at the bottom. The leftmost input column shows the initial misaligned red and green point clouds. Then, moving to the right, we see results from various deep learning techniques, such as DCP, PointNet-LK, RPMNet, and DeepGMR. And once more, the far right column clearly demonstrates that exponential similarity matrix iterative closest point achieves a consistently better, more accurate alignment for all three objects. Alright, so we've seen exponential similarity matrix iterative closest point outperform both traditional and deep learning methods in general alignment tasks. Now, Figure 6 really hones in on a specific and very common challenge, its performance when there are outliers present. Outliers in this context are data points that are kind of stray or erroneous, sitting far away from the main shape of the object, often due to sensor noise, and these can really confuse many alignment algorithms. The top row here shows various input objects, like a handbag, a vase, and a bottle, each with those red and green point clouds initially misaligned and, crucially, corrupted with these outlier points. Then, looking at the bottom row, we see the output. And impressively, exponential similarity matrix iterative closest point still achieves a very clean alignment of the underlying objects, effectively ignoring those noisy outlier points. That robust performance, even with significant outliers, really underscores the strength of exponential similarity matrix iterative closest point. It's not just holding its own. It's often outperforming both traditional and newer deep learning techniques for 3D point cloud registration. This kind of reliable alignment is so important for fields like autonomous navigation and creating detailed 3D models. Well, that wraps up our look at this intriguing paper. Thanks for joining me on the AI Research Roundup. I'm Alex. Catch you on the next one.